Okay, good. So we're gonna continue with public encryption from last class, and I promised to show you a fourth public encryption scheme, and that's the topic for today. I'll have to do more math to kind of set it up, and this is math that we'll end up using later when we eventually, at the end of the class, construct a fully homomorphic encryption scheme. So it won't all be just this one lecture. All right. So far, we saw public encryption. As I would say, public encryption. Really, the absolutely crucial thing to remember here, we tell our students in the undergraduate algorithms class, or perhaps also the complexity class, that there's one thing you remember out of this class. It is not to say that NP is not P. Yes, I mean, you have to. One of the basic things you should remember is, at least a basic thing you should remember from here is, when you want to encrypt with RSA, you should not be doing the message to the power E mod n. That is not the way to introduce RSA, because it reveals all kinds of information. So make us proud, make us embarrassed. Okay, so Robin. Yes, Robin is the other one that also falls into this methodology. And then we saw the Goldwasser-Mihaly encryption scheme. This is using the hardness of the quadratic reciprocity problem. And finally, the L11 encryption scheme, or rather which is more or less equivalent to the Diffie-Hellman heat exchange. Of the decisional, pure on the hardness of the decisional Diffie-Hellman assumption. This is the RSA assumption, and this is the factoring. This is the list of public encryption schemes we've seen so far. We'll do one more. And that is using the hardness of a problem called learning with errors. Okay, it's a new problem. What is learning with errors? I have to fix parameters. To define this problem, I have to fix certain parameters. One is the n, the dimension parameter, which you'll see what it is in just a second. And you should really also think about this as the security parameter. In other words, the larger this is, the more secure; the smaller this is, less secure. This defines the security of the problem. Q, which is the modulus. Again, you will see what this is in just a second. Set it up, yeah. And B is the error parameter. And here's the problem. Imagine that I have a secret in my head, and the secret happens to be a random vector of length n, n-dimensional vector. Each entry of this vector is drawn randomly from ZQ. So here Q is very different from the Q, the modulus, the kind of things we saw in the past, where in the past our Q was 1024 bits or 2048 bits or whatever. Then you can really think about Q as being, 7 bits. It doesn't really matter. That's not where the hardness comes from. The hardness comes from the fact that n is very large. Okay, so I have a secret in my head. ZQ to the n, and this is random equation. And you get, you as an adversary, get orbital access to it. in the following sense, you can press a button in this box. And each time you press a button, you will get a random vector A, chosen randomly from z equal to the n. So far, so good. Right? There's nothing to do with the secret, but you also get A in a product S. You get a pair of these guys. Right? You get a random vector, which defines a linear equation, if you will, and the inner product of A with S, which defines, this linear equation. If you plug in the secret, what is the output? That's A in product S. Yes. So you are a polynomial time adversary, probabilistic polynomial time adversary, and so you get to query this polynomial many times. What does polynomial mean? Polynomial in n, polynomial in log q, the description length of elements in ZQ, and that's it. Right? So you can get run for poly n log q time, and the assumption is that you can't recover what is the secret inside my head. If you keep pressing buttons, I keep giving you these guys, these things, you can't recover. All very happy with this? Yeah. How many people are happy with this? How many people think that this assumption is true? Okay. So, how many people think that this assumption is false? Wait a second. I mean, you can't all be undecided. Yes. Why? Because if you say false, I'll ask you why.
Yeah, I'm sort of forgetting exactly what it is, but we can do some sort of orthogonal vectors computation and recover it.
You can recover S. Okay. So the question is how? Yes.
If it's a system of like n linear equations, then you just need like n queries to be able to solve it.
So what does each query give me? It gives me one linear equation, right? So think about A as sort of A1, A2 up to AN. A in the product S now is A1 S1. S is S1 S2 up to Sn. So A in the product S is A1 S1 plus A2 S2 plus A2 AN Sn. Mod Q, yes? The next time I get another linear equation, I know the coefficients. I think of these as the coefficients of the linear equation. This is the variables. I get another linear equation, A1 prime S1, the same S1, plus A2 prime S2, and so on and so forth. And I get n of these linear equations, and we know that if I have a full rank set of linear equations, I can actually, the secret is uniquely determined, number one, otherwise there's no hope to recover it. And two, you can recover it in polynomial time. Just use Gaussian elimination. It's one way to do it with canonical. The typical Gaussian elimination that you saw was probably over the real numbers, but everything that works, well, everything in this class that works over real numbers also works small scale. Gaussian elimination works small scale. Okay? We can recover. Just need to solve linear equations. And solving linear equations, mod Q is just as easy as it is over the real numbers. Great. So this is if the system of linear equations is a full rank system, right? If the second A1 prime, A2 prime is like 5 times A1, then A1 prime is 5 times A1, A2 prime is 5 times A2, A3 prime is 5 times A3, then this new equation doesn't give me any information beyond the old one. But it's very unlikely that that sort of thing will happen. So you will get a full rank system as long as you make slightly more than n queries. 2 n queries should be good. So this is broken. It's totally broken. And this is I'll call the learning without errors problem. So lead you on to what I'm going to say next. Learning without errors is insecure in the most ridiculous possible way. So let's do learning with errors. W stands for with. Okay, so here what happens is I make a tiny change. I need space. So, what I'm going to do is I'm going to still give you the A randomly from ZQ to the N. I'm still going to give you, still going to compute A in a product X, but I'm going to add a number E. So this will still give me a number in ZQ, mod Q, so it will still give me a number in ZQ. Where what is E? Where E is drawn at random from the range, I haven't used B anywhere, yes? From the range minus B to B. So think of integers. Everything is an integer, right? So think of integers in the interval minus B up to B, so 2B plus one of them. Pick a random one of these guys, add it to this equation. Add it to the result of this equation. Give it to me. Of course, I don't tell you what E is. I tell you what E is, you're back to the learning without errors. And this, you can do it, your polynomial time, you can do it polynomially many times. Now try to find the secret. This is the learning with errors problem. The observation is that, Gaussian elimination fails miserably when you have sort of erroneous linear equations, mod Q. And we believe that essentially every algorithm fails badly in this evaluation. I want to tell you, I'll tell you what badly means in a minute, but this is the assumption. Yes? Good? Right. You should ask, for what parameters N, Q, and D is this problem, number one, even solvable to begin with, right? For some parameters, no matter how powerful you are, you won't find the exact solution. For some parameters, you can actually find solutions in polynomial time, right? Where we want to be is in the middle, where there exists a solution, a unique solution, given all the information I have, but it is computationally hard to find. Sort of like the one-way permutation setting, yes? There exists a unique preimage, but it's computationally hard to find. That's where we want. So let's kind of think through this for a second. What kind of, how would you set the error parameter in a way that no one can find the S, no matter how powerful they are? Anyone? The entire size of the group, essentially. So I would pick E. So if E is very large, by this I mean really very, very large. It's really random over the group. So that is B is, let's say, Q minus 1 over 2, I think. Right, so think of Q as an odd number. If B is Q minus 1 over 2, the size of this range basically covers the entire ZQ. So then every sort of sample I'm getting from this oracle, from this box, is a random number. Say in a product S plus E, which is a totally random number. So of course I won't be, no one will be able to solve it. Then this is information theoretically impossible. Yes? And therefore, we will set B to be something like, to be less than Q minus 1 over 2, really. And typically it's something like Q over 4, something like that. There's nothing very special about 4. You can make this 2.1, and that would work just as well. So anything that, yeah? So what one can show is that if B is less than that number, right, let's say Q minus 1 over 2.1, then given sufficiently many equations, given sufficiently many calls to this oracle, the S is uniquely determined. So this is something one can show. I am not going to show it here. I'm not going to show it here. You can show it. And therefore, will anything less than the trivial thing is already parameter setting, where given unbounded power, you can sort of find what the secret S is. But computationally, so if you have your PPT, good luck to you. Okay, so that's the first observation. And the second observation is that if E is very small, what does very small mean? 1, I guess. I can't go. But if it's 0, then there are no errors. Yes, I mean, if it's 1, that's the next sort of best setting. Then what do you do? Then again, given enough sort of samples, the secret is S is uniquely determined. But the question is, can you find it, involve it? Good. So this is, okay, what do you guys think? What is the crowdsourced opinion? Yes.
Well, then there aren't a whole lot of errors there can be, so you can just sort of try each one.
That's not entirely true, right? I mean, for each equation, there are only 3 possibilities for the error, right? But well, what would you do, right? I mean, if you can guess what the error is, right? But from one equation, you cannot even uniquely determine this. There are exponentially many possibilities for the secret. So you won't know what the right one. Now, if you take 2 equations, then the secret is a little bit more uniquely determined, right? But then you have now 9 possibilities for the error, right? So this is a conundrum, right? I mean, if you have more equations, then the secret is, there are many. So if you forget about the error, there are many linear equations. So the secret is getting more and more uniquely determined. But then you will have to guess more and more and more of the error. You know what? Let's keep going. So let's say, about n samples, the secret is uniquely determined. You have to trust me on this, right? What is the attack? What is the running time of your attack? So let's say, you have n samples, yes? And you do your strategy, right? What is the running time of the attack? You have to guess 3 possibilities, essentially 2b plus 1 possibilities. So we have to guess it in time. Say again?
3 to the end.
3 to the end, exactly, right? So you guess all the possible errors. You try to find, if the error were this, what would be the right S? Right? If you guess correctly, then you will be able to check. Right? Think of it as I have 2n equations. I have, let's say, 3n equations. I keep n equations aside. Just take 2n equations. Trust me that the solution is uniquely determined. Now you enumerate overall 2n, so 3 to the 2n. So that's a way to solve it, but it's exponential time. Exponential there. That's a way to solve it, but not a polynomial time. Given this is a claim I want to make. Let's see how this works. Okay, so certainly not enumerating. And I have to tell you what enough is. Enough cannot be 2 to the n. Better not be 2 to the n.
Does it also say something about Q here? Q can't be anything.
Q can't be anything.
Q can't be 2.
Q can't be 2.
It also can't be 3.
If Q is 2 and B is this, again you're randomizing over the entire group.
So no, so you want to say something like, there's a really large constant Q, this will work.
Yes, good, okay. We'll get there in just a second. Okay. samples. Q is bigger than B essentially, or 2B plus 1 or something like that. Okay, so we'll see the attack. All right, let's do it. So that's the. So this is a an attack due to Aurora and Gay. Yes. So let's fix the setting of B equals 1. Yes. So what do you get? You get every time you get A in a product S plus E, and this E is either plus 1, 0, or minus 1. It's not we chosen, I don't know what it is, but it is one of these three numbers. Yes. All 1 cube, of course. Let's call this number B. It's a single number, right? Call it B. So, I'm going to say something trivial, okay? Then something slightly less trivial, and then we'll have the attack. So what can I say about B minus A in a product S? Of course, you don't know this is what you get, you don't know what S is, you don't know what E is, yes? What can I say about B minus A in a product S? So say again? 0. Not always. Is E, yes. And so it's either 0 or plus 1 or minus 1. Yes, I don't know what it is. If it were 0, that's the setting of the learning without errors. So then I will do that. What can I say about the following quantity? Which I'm going to write down in a second. This is times, right? Times. If you want to, it is always 0. Because B minus A in the product S is either 0 or 1 or minus 1. One of these terms will go to 0. So this is equal to 0. So each sample turns into an equation of this form. And what do you know in this equation? You know B, you know A. You just don't know what S is. That's all you don't know. So this is not a linear equation in S's, in the coefficients S anymore. It's a degree 3 equation. It's a polynomial equation of degree 3. Okay? Because you can expand it out, right? Each term will be of the form Si, like coefficient, times Sj, times Sk, times some constant. Add it up. Yes, that's an equation. So I'm not going to write down the whole thing, but you see it. Now, okay, voila, you have many samples. Each sample is a polynomial equation, right? You get many polynomial equations, degree 3, multivariate polynomials. So there are many n variables, degree 3. Let's solve it. No? Except, that doesn't turn out to be that easy. Solving linear equations is very easy. Solving quadratic equations, in the worst case, is NP hard. You can reduce SAT to solving a system of quadratic equations, basically. So it seems like we went all through, we got to nothing, basically. Except the one observation here is that you can actually solve a system of polynomial equations, n variables in degree 3, if you have sufficiently many equations. That is the one observation that we need to make this argument. So if I give you n equations in n variables and degree 3, there's no way you can solve it. In fact, if you solve it, you solve NP. Yes. But if I give you n cubed equations in n variables in degree 3, I claim that you can solve it. So if this little guy here asks for n cubed samples, each sample is something else from, so then you get n cubed polynomial equations. And of course, everything is polynomial here. He can carry out this attack, right? Yeah. The question is how. Okay. Claiming is one thing, proving is another. Okay. So let me sort of write down this this equation a bit more explicitly. So turn into this is turn into polynomial equations. Each sample turns into polynomial equations. Number two, sort of rewrite this. Yes, rewrite this. So this is going to be a big sum over ij and k of some coefficients. Let me call them alpha ijk. So this is, you can compute it. Anyone can compute it. In fact, the little guy can compute it. So public coefficients. Si times Sj times Sk. Right? Plus a bunch of other things, right? I mean, beta ij Si times Sj, because these things will have sort of degree 3 terms, degree 2 terms, degree 1 term, and a constant term. Yes, if you blast it out. Plus the sum of gamma I Si plus delta equals 0. That's the way this is going to look like. This is just one equation in many equations. Now what? Now I'm going to do the following trickery. That's called linearization. Okay, linearization. Which says, you know, there are these sort of terms here, monomials, Si, Sj, and Sk. Si times Sj times Sk. Give them a name. Okay. Si times Sj times Sk is a variable. Call it something. Okay. Call Si times Sj times Sk equals, call it Tijk. Si times Sj Tij. Then you have Si's. Then a constant. Yeah, I mean, I'm just renaming everything. You know, product of things, I'm just giving them a unique name, just renaming variables. Now look at that equation, that polynomial equation. Yes? That is a linear equation in the variables t's, by definition. So now I have an equation. Each equation of that is of the form alpha ijk, tijk. This is a variable, single variable, plus the sum of beta ij, tij, also a variable, plus the sum of gamma I, ti. This was always a variable, plus that. So this is a linear equation. The only problem with, I mean, I could always do this, right? So it seems like I'm giving you a recipe for solving polynomial equations. Yes. Yeah, that cannot be. I cannot solve NP in half a class. You know, it doesn't work. What is the problem with? So now the strategy is clear. Yes, I mean, I have a system of linear equations. Just solve it using Gaussian elimination. Find solution. Find Tijks and Tijs and Ti. Yes, and you can read off from these things what S's are. Yes, because in particular, because some of these T's are equal to the S. So just read off. That's how we're going to break LWE. Yes. So this cannot. There is a problem here. And what I'm saying is way too general to be true. Why is that the case? Anyone see? Yes.
Well, one thing I see, it's not clear in general that the distribution on equations over TIs are in general going to be linearly independent. So you might not always.
Fair thing. That's a very good point. Excellent point. Want us to show that these guys are, of course. That's an issue that I'll sweep under the rug. Okay, one can, and it's an important issue. Yes, I mean, otherwise you just cannot even solve the linear equation. It's an important issue. You can show it, but I'm going to sweep it under the rug. There's a bigger issue. Anyone see? Yeah.
I don't see it necessarily doesn't generalize, but I think there's something to verify things like Tij is equal to Ti times Tjk.
Of course, right? So look, I mean, I'm going to write down the system of linear equations. I'm going to solve it for these Tijks and Ti's and Tijs, right? I get a solution. But Gaussian elimination that didn't promise me that these things are consistent. For example, I should have that Tijk times TL equals Tij times TKL. It has to be, if it is correct, it has to satisfy a bunch of these consistency equations. Austin?
Can't we say, like, if it actually came from those assets, then?
Beautiful. Okay. Very nice observations. Okay. So, very good. Yes. Let me observe something before I dig into it. How many variables are there in this equation? How many linear variables are there? Many, n cubed actually. N cubed. Yes. So, if I have fewer than n cubed equations, right? Then there are, so the number of solutions, Tijk, Tij, and so on and so forth, is large. You know, if I have like n over 2 linear equations in n variables, right? There are typically 2 to the n over 2 solutions. Right? There are many solutions. This is the set of all solutions. If the number of equations is little o of n cubed. In fact, if it's even less than n cubed. Yes? There are many solutions in Tij, in the T's. The right solution is one of them. Right? Because I know that if you instantiate these guys with the right products, that will be a solution to this linear equation. It's just that there are so many other guys kind of clobbering up the space that, number one, Gaussian elimination is unlikely to find this right solution. In fact, it won't. If it did, we would solve NP again. That's the issue. Yes? Yeah. Does this address your comment? So you said S is one of the solutions. Beautiful, yes, but there are many other solutions. That's the problem. And you said Gaussian elimination, you need to do consistency checks, because not everything that comes out of Gaussian elimination is a solution, precisely. But then the thing is, once the number of equations goes above n cubed, sufficiently above n cubed, the number of equations is not this. The number of all these other guys will kind of get weeded out. The only thing that will remain is the one solution. So Gaussian elimination has no choice. That's what we want. That'll make sure that, one, that the solution is uniquely determined. Two, because P is so large, you can't find it in full, at least with this attack. More generally, this learning with errors problem is related to something called the shortest vector problem on lattices, which tells us exactly what parameter regimes these guys are solvable, what is not solvable. And this guy seems like the canonical kind of regime where all attacks fail. Not just this guy, all attacks fail. All right, so now we have a problem. This is more complicated than factoring, yes? I mean, we spent 45 minutes talking about it, as opposed to half a minute saying factoring, right? But the good thing is that, two things. One, it's not something that we'll go into in very, very much detail in this class. But, you know, the first 4 encryption schemes are completely broken if you have sort of quantum computers, quantum algorithms. If you have algorithms that can simulate quantum, if you have machines that can simulate quantum algorithms faithfully, then the first 4 encryption schemes are lost. And that's essentially due to Shor's algorithm. Shor's algorithm for sort of factoring and essentially discrete logarithms will destroy the first 4 of these things. Or actually, all of these things, like all 5 of these things. On the other hand, this guy, whatever I'm going to build, seems to survive quantum algorithms. And this is essentially 1 of 2 or 3 examples which do survive. That's one. It's one reason to study this. The second reason to study this is that it lets you do homomorphisms, which you might say, what's the big deal? Because we saw that essentially all these encryption schemes are homomorphic one way or the other. But if you want to be homomorphic with respect to both additions and multiplications, and with respect to anything you want, you need this guy. So there are two very good reasons to study it. So we'll start doing it. And good. So let's first kind of build, for building things. I told you, two very good reasons to study this. Yeah, so you might say, why aren't people kind of like, like going all crazy and sort of throwing away factoring and using this? Many reasons. The practical reason is that the entire internet kind of runs on Parsec and Diffie-Hellman. You can't, at the drop of a hat, replace these guys by something else, which I'm going to describe. Number two, because people have spent much greater deal of time trying to break factoring and Parsec than they have trying to break this. So that's why people have paused, and studied this a little bit more. Okay, very good. Okay, so to build encryption schemes, secret key, public encryption scheme, I have to introduce a variant of this assumption called the decisional LWE assumption. So you've seen many variants of sort of decision and search problems, right? And what I'm going to describe should come across as sort of a natural variant. Secure, unclear to you yet, but natural variant. Okay, so again, there is a time distinguisher. And now the game is either it gets Oracle access to this Oracle, so that gives it A and A in a product S plus C, the same way as here. Or it gets Oracle access to something which has, I suppose it has a, oh, it's equal to the n, yeah? In its head, but it gives the adversary A together with a number U, and U is uniformly randomly chosen from CQ, right? One guy tells him precisely what this guy says, and the other oracle would tell him just random numbers. Okay? And this adversary lives in either this world or this world. It doesn't know which oracle it is talking to, and its goal is to distinguish. It's to say, which world am I living in? Right? That's the decisional LWE. Makes sense? Good. So I claim that if you can solve the search LWE problem, you can solve the decisional LWE problem. Yeah? Is it clear? Why? Yeah. Can anyone tell me how? If you can solve search, well, that guy I'll call it search LWE. Search within brackets LWE. You can also solve decisional. How would you do it? Decision LWE. That's what you want to solve. Yes. Well, think about it this way. If you can break, 1 second, if you can break one Venus, yes, wasn't this a question? If you can break one Venus, you can break pseudo-random swarms. Yes, ask.
Oh, you just try to solve it and like they get a lot of queries. If you get a lot of queries and the right answer will not satisfy all of them, this will just fail and the left one you will find that it's not. Yes.
Good. Excellent. So what Arsene is saying is, well, let's imagine that you ask a bunch of queries to your oracle. You don't know which oracle it is. Just ask a bunch of queries. Let's say the first 100n of these queries you ask, you solve you run the search algorithm, it'll give you an S. Yes. You don't know if that S is right or not, but you can check always. Use the next 100 n equations, plug in the S here in the A in a product S spot, subtract it from the second number, see if the number is small. If it's small for all of these guys, this is the solution. Yes. Good check. On the right-hand side, you do the same thing. You might get an S, but the rest of the numbers are random. There is no way you're going to, it's going to work. That's the, yeah, that's the roughly idea. You have to be careful that you pick these numbers to be large enough so that things are uniquely determined. That's the easy part. The more interesting part is the opposite. It turns out that this is an if and only if. You can solve decisional LDPV, then you can solve search. That is not clear. It should be clear. It should be completely clear. Right? So this is sort of saying, this is sort of proving the hardcore bits kind of statement. Right? You have an algorithm that distinguishes certain things. You want to use that to predict certain things. Yeah, it's morally important. Does anyone see, given this spiel, does anyone see how to do this? Right? So you're in this world, and all you have access to is someone. You keep getting samples. You know that you are living in this world, but you have an algorithm that will distinguish this from this. If you want to somehow use it. Okay, it shouldn't be completely clear to you. Or is it? Any ideas? Yeah.
You get something from up top. You give it to the guy on the bottom. He tells you, yes, put them into your polynomial solving algorithm. He tells you, no, don't put them into your polynomial solving algorithm.
So remember that the one on the left, yes?
Yeah.
The one on the left will only work if the errors are relatively small. So the running time of the attack on the left is n to the power 2b plus 1, where b is the bound on the error. So I am by default going to set b to be n. So then it's n to the n. So that guy is not going to work. Yes. That guy is not going to work. And in fact, to mount that attack, you don't even need the decisional algorithm. You can just kind of make a bunch of queries to and just do it. So, but the point is, you want to use an algorithm that distinguishes between two things meaningfully. Any vague thoughts? I don't expect you to come up with the answer. It's not trivial. Yes?
You could always create S plus S prime and S prime buffer.
S plus S prime?
Like you could emulate that oracle.
Given that oracle, you can emulate an oracle for S plus S prime, you're saying. Where S prime is maybe random or you're choosing or whatever. True, right? But you want to invoke a guy here, right, who either gets something of the form you're creating or something random, and he distinguishes between two. Now the point is that if you know which oracle you're emulating to this other guy, well, you know the answer he's going to give. So you shouldn't know what you're doing in the first place. Right? Otherwise, you don't. If the guy is no use to you, you can do it yourself. All right. So let's do it. So I'm going to show an outline of the attack. Attack is the reduction. Reduction from search to decisionality. I'll miss all sorts of important details. some of which you will point out to me. In any case, the full proof will be in the lecture notes. But I want to give you the idea of how this is done. Right? So I'm going to use something like your process. Okay. So what do I do? So I'm an algorithm. I want to solve search. Yes. So I get a bunch of samples. I get polynomially many samples. So I'll get the first, I don't know, 2n samples or something like that. Why 2n? Because perhaps the decision algorithm will already distinguish between the two, given 2n samples. How many ever samples the decision guy asks for, get that many samples from the search algorithm? Pick first. And now guess. Okay? Just guess. Just guess what? Guess that the first coordinate of the secret is, pick a number. 5. Make a guess. Okay. Make a guess. You got these samples, and depending on your guess, do something to these samples. Okay? Do something to these samples. And then feed it to the distinguisher. What we will prove is that if your guess was correct, somehow magically these samples will look like they came from here. If your guess was wrong, the samples will look like they came from here. So now the decision algorithm will tell you, was your guess correct or not? Yes. If the guy tells you, is it correct or not, I can enumerate over all possibilities. How many possibilities are there for the first coordinate? There are q possibilities. The total n times q possibilities is all polynomial in n. I go through each possibility for each coordinate, right? I'll use this guy to tell me, did I guess correctly or not? That's the strategy. That's the way I'm going to use the decision algorithm. I'm going to make a guess. I have no clue if it is correct or not, and then use the guy to tell me if I guess correct. Okay? So let's do it a bit more carefully. So here's the subroutine. Gets us input A1S plus E1 up to A, call it M, MS plus. So where do these things come from? They come from the search oracle. Right? I'm trying to solve the search problem, ask the search oracle, get these guys, now do something. So what do? The input, this is the first part. The input is also a guess. What is a guess? The guess says, is S of I equal to C? So C is a number in ZQ. Yes, I is a number from 1 up to n. Right? So the total number of possibilities is for every I can make q guesses. There are n I, so n times q guesses. That's the total number of guesses I can make. For each of these guys, I'll do the following. Okay, then this is the important part. I have to show something about whatever I'm doing. So I'll pick vectors So I'll change A1 to A1 plus R1, sort of like what you said. You know, I'm going to add a random vector to A, just going to completely randomize it. Except I'm not going to do that. I'm going to add R1 times the vector 0, 0, 0, 1, 0, 0, 0, and 1 in the ith location. Okay? So in other words, I put a random number R1 in the ith location of this vector and 0 everywhere else, and this vector I add to A1. Right? And call this vector A1 prime. Yes? So A1 prime is also random from the adversary's point of view because I took a random vector and added something to it. Of course it is not. Yes, and now I'm going to create B1 prime, which is, well, let me see. how would I create V1? V1 prime is supposed to be A1 prime in a product S plus noise. So supposedly A1 prime in a product S plus, let's say, the same noise, E1. I'm not going to muck around with the noise. But what is A1 prime in a product S? It is A1 in a product S plus this guy in a product S. But what is this guy in a product S? It's R1 times S1, the coordinate of S. Because that's the only thing that matters. If you take the inner product of this with S, the only thing that matters is the coordinate of S plus E1. This is what I want to create, yes? But I don't know what, I can't go from this, A1S in plus E1, to this, because I don't know what SFI is. But you know what, I made a guess. Okay, so let me double down on my guess. Okay? So let me define V1 prime to be V1, which is this. So this is V1, this is V2 up to Vm, plus R1 times C is my guess. Okay? That's what I do. So I get A1 prime, V1 prime. I do the same thing with A2 prime, V2 prime, same thing with A3. In other words, pick random R every time, add it to A, and then add this correction factor to B. Keep doing it. So now you get many n samples, whatever you started with, you get it. Feed it to the decision order. Okay? If you guessed right, this looks precisely like LWE sample. That's what it is. But if you guessed wrong, I want to claim that this looks like random nonsense to the others. That's what I want. Yeah, so the first part is clear. I mean, the way we set it up, if my guess C was actually S of I, then this is precisely what I'm supposed to set. So A, if C was in fact equal to S of I, A1 prime, B1 prime, up to AM prime, BM prime, look like LWE, look like Oracle 1, LWE Oracle. The output of the LWE Oracle. B, if C is different from S of I, then these guys look random. In fact, they are random. There's no look, they are true. Okay. Why is that the case? Because let's sort of rewrite this, yes? So let's rewrite this as B1 plus R1 times S of I plus R1 times C minus S of I. Yes, it's the same thing. I mean, I added something. This guy is supposed to be A1 prime in a product S plus E1. Yes, that's the calculation we did. And the point is that given A1 prime, right, given A1, the sum of these two guys, that's A1 prime, R1 is completely hidden. You don't know what R is. No one knows what R1 is. Because it's like taking this vector which has information about R1 and adding a random vector to it. Of course, there's no information about R1. R1 times. So it is like an LWE sample plus a completely random number. Yes, R1 is a completely random number conditioned on everything else you know, and this is a non-zero number by definition. See, we are in a case where I guessed wrong, so C is different from S of I, so C minus S of I is not 0. So any non-zero number times a random number is random if
Modulus is prime.
the modulus is prime. Exactly. Yes, otherwise this is not necessarily true. Yes. I declare victory. So the only thing I have to change here, make this go through, it's prime. You can also make this a more complicated version of this reduction go through for arbitrary Q, but for now this is good. Yes, so the principle here is this applies to all over the place. In fact, it should apply to your problem set. in particular, immediate concerns. The idea is that if you have a distinguisher, how do you use it? One way to use it is to solve a search problem. I get a search problem, I muck around with it, right? Yeah, I have two possibilities depending on something I don't know. And, one possibility gives me the one distribution, other possibility gives me the other distribution. The distinguisher is going to tell me whether I'm right or wrong, or which possibility I'm in. And that's one bit of information. Keep doing it many, many times to recover all of this. Good. Yes? Go back and read. So we're going to post the notes on the search term decisions. All right. So given this, what do I want to do? I want to do two things. One, I want to construct a secret key encryption scheme and a public encryption scheme. Okay. So what's the use of hard problems are useless to me as a cryptographer unless I can construct stuff. Okay. Let's do a secret key encryption. And this should be completely obvious at this point. It's completely obvious. It should be reasonably clear how to construct a secret key encryption, right? So what do you need? You need a secret key. You need a key generation algorithm that generates a secret key. You need a way to encrypt. And let's say, you just want to encrypt one bit. Bit, number, doesn't matter. Let's say 1 bit. Okay, this would be minimum. And the decryption algorithm. So how would I proceed? Let's say, what is the secret key? First things first. I don't know, I want to use this guy, yes. There is only one thing that is secret here.
S.
Good, very good. So pick an S randomly from ZQ to the end and call that your secret key. Now, how would you encrypt? Well, I want to use the S somehow. So, have any guesses? You can say the very first thing, and then I'll complete it. Promise you. Yes, Arsen?
Like, generate a lot of those queries out of the oracle.
Let's say just one for the moment. Yeah. Okay, so generate. Okay. So you promised to tell me the first part, and you don't tell me the first part, correct? So generate one query, which is the random A. Yes. Together with A in the product S plus E. Where E is again chosen from the error distribution for a sufficiently large B, so these attacks don't apply. Okay. Now someone complete the second part for me. I didn't use a message. Yes. Say again? XOR with the message. Except XOR is a sort of mod 2 operation. I'm in mod Q, so yeah, go ahead.
Oh, I want to say, maybe if we're encrypting one bit, then just decide whether it's like completely random or it's like AS plus E.
All right, very good. So this is a good encryption scheme, very good, but that's not what I'm going to do. So Arsen's encryption scheme is, I said for some reason, I shouldn't have, I'm only going to encrypt one bit, right? Arsen says, if the bit is 1, then output this. Okay, so this is an encryption scheme. If the M is 1, then output this. If M is 0, then output A together with the uniformly random number. Yes? And what is the decryption algorithm? Check. Take the inner product of A, the first component with S, subtract from the second guy, check if it is small or not. That's it. Okay? There's one problem with this, one problem with this scheme, which never appeared in all the previous schemes, which is what? No security. Forget it. Security is obvious. It's completely obvious. Is it correct? Is it? Say again?
How do you decrypt it?
How do you decrypt it? Okay, good. So decryption algorithm. So what is the ciphertext? It's a pair of things, right? A vector and a number. Your secret key is a vector. Is S.
You're just going to generate a bunch of samples and then.
No. Okay. So here's the decryption algorithm. Take the vector in a product with the secret, right? Subtract it from the second component. So if it looks like this, then what you're supposed to get is E, which is a small number. If it looks like this, then you get essentially a uniformly random number. So now you say, well, I get a number. If it is small, in the sense it lives in minus b to b, the range minus b to b, I'll say the message was 1. Otherwise, I'll say the message was 0. Yes. Certainly, one of these things is correct. If you actually get a message, if you actually get an encryption of 1, you will say 1. But if you get an encryption of 0, you might still say 1 some of the time, because a uniformly random number has some chance of falling in the small range. That's one problem with this. There's a way to fix it. It's not, right? And how would you? Send a lot of them. Yeah, okay. So now that we are going back to what you said before, right? So if the message is 1, send a lot of these. If the message is 0, send a lot of these. So now what's the chance that all these uniformly random numbers kind of fall in the same place? It's exponentially small. So you will still have an error, but an exponentially small decryption error. Yeah? This is... You know what? I'm not happy. I shouldn't be not happy because exponentially small never happens. So for all practical purposes, should be happy. But let's say I want perfect decryption. I don't really care because I want to move to a different encryption scheme which has other properties. That's why I'm saying it. But this is a perfectly good encryption scheme. I want another way to do it. And that time, let me go back to what you said. What's your name again?
Shashank.
Shashank. Okay, good. It's an XOR with a message. XOR is a mod 2 thing. Now we are working mod Q. So plus M. Yes. So now how do you decrypt? Again, you have two guys. Take the first guy in a product S, subtract from here. You get E plus M. And now what? Okay, good. So this is incorrect in a more egregious way than Arson's scheme was, right? In the sense, I either get an error, a random number from minus 2b plus 1 to 2b plus 1, or I get that plus 1. What's the chance that I can distinguish? Nothing. 1 over polynomial. So that I don't want to do, but let me actually error, instead of before adding the message, let me error correct it. Let's say Q is odd, right? So Q plus 1 over 2. So this is a midpoint of 1. Okay, so now I claim we are in shape. Why? Because I take A in a product, I subtract, I get E plus M times Q plus 1 over 2. So this guy lives in the 0 Q minus 1 range. If the encryption is an encryption of 0, then this guy doesn't exist, it's E, basically. E is a number from 2b plus 1 to minus 2b plus 1, which is Q minus 2b plus 1. Yes? So this is an encryption of 0. This is E plus MQ plus 1 over 2, if M is 0. And if M is 1, then it'll look like Q plus 1 over 2 plus minus B. Right? So this is Q plus 1 over 2 minus 2B plus 1, and this is Q plus 1 over 2 plus 2B plus 1. Yes. This is the E plus M Q plus 1 over 2 if M is 1. So of course, if I set B to be small enough, which is basically smaller than Q over 4, then you're good. You can perfectly distinguish between these two cases. Yes?
Just for a better visualization, can you give an example of N and Q that are actually used?
That are actually used? You mean concrete numbers or asymptotic?
Concrete.
Concrete numbers, good. Yeah, so here it is. N is, let's say 512. Yes? Q is well, I believe 127 is a prime or not? Are any of you primality testers? You know, like fast primality testers? 127.
It is prime.
Okay, good. 127. Yes. And B is fairly small. Set it to be 8. Let's say. 8 would work for this because then 2 to the 10, 2 to the 10, something like 12. Yes. Because the obvious attack is n to the 2b plus 1. We want that to be bigger than like 2 to the 128 or whatever. Okay. Yeah. Something like this. So obviously, you know, b is less than q over 4. Right. So then you get correctness. You get security because n to the b is extraordinarily large.
Q is 127 just for computational.
Yes, yes. You can set q to be very large. That's okay. But yeah. You could set q to be the RSA number, the RSA prime. That's okay. That's perfectly fine. But why would you do it? You know, doesn't seem to help for security.
This is that it's a small 2 to the n minus 1 type, right?
Say again?
The reason that it's a small 2 to the n minus 1 type, right?
It doesn't have to be any. It doesn't have to have any structure you want. Just pick a prime. That prime has to be large enough because number 1, b has to be large enough. Otherwise, you have attacks. And q has to be bigger than b because otherwise you won't get correct. That's why q has to be large enough. Right? That's it. To the 10, to the 9, to the 9, to the 9, 12, something like 2 to the, or actually even better, 2 to the 200-ish is n to the b, 2b plus 1. So that covers our basis. And then you can set q to be anything that's larger than 4b, essentially. So a prime that is larger, pick a prime that's larger than 4b, any one that you want. Good. All right, so that's the, this is correctness, perfect correctness, yes. And security is LWE, because this guy is, by decisional LWE assumption, this is a one-time pad. If you have a one-time pad, we go back to Shannon and say things are very good. Okay. I'm being very sort of succinct, concise here, but at this point, you should be able to kind of write this down. So yeah, so that's secret key encryption. 10 minutes to do public encryption. Question? Yes?
It ends with a 2b plus 1, the lower bound.
N to the 2b plus, is it a lower bound? No, it isn't. It isn't. And we don't know how to prove lower bounds in any of these attacks. We have essentially sort of 3 types of attacks. One is what I showed. There are 2 other types of attacks. And you can say what is the min of the complexity of these attacks. That's the best we know how to say. We don't know how to prove lower bounds. Right. If you prove a lower bound, then you in particular prove that P is different from NP. Is that what you're asking?
So how do you know B equal 12 is enough?
Is enough. Good. Excellent. So the way that is to say, look, let's set these parameters. Let's run the polynomial solving attack. Right? Let's compute what is the complexity. I can't run it. I compute the complexity. Let's compute the complexity of another sort of type of attack, which is basically an attack that finds shortest vectors and lattices, which I haven't told you what it is even. Let's compute the complexity. Let's compute the complexity of attack number 3, attack number 4. If all of these things are bigger than 2 to the 128, let me say. It's a heuristic, yes. We don't know how to prove lower bounds in this world at all. Nothing we are doing in cryptography is, so far, except Shannon, is provably absolutely secure. We have to assume something. So you could ask the same question about factoring. How do I know that 1024-bit sort of product of primes is hard to factor? I don't know. You run the quadratic C, you run the number field C, you run Lensstrass algorithm, delta curves. You say all these things run in more than 2 to the 128 times. 2 to the 128 times. Ergo, QED. Yes? It's the same story. But you have to identify attacks. The thing that is a little bit unsettling about these kind of crypto systems is that, you know, for factoring, people have spent 40 years. People, as in people we know, and people we don't know. Same thing I say. They spend time tracking these things, and so far, to the best of our knowledge, hasn't been attacked. That's not quite the case with LWE. You'd still need time to kind of like come up with new algorithms to break these things. Then we'll know. Okay? Shortcuts. Long answer to shortcuts. Okay, good. So public encryption. Next step. In fact, actually, I'll tell you one thing. The American National Institute of Science and Standards and Technology is the one that standardizes these encryption schemes, including RSA, Diffie-Hellman, everything. So now they have a competition where you can sort of submit proposals for that look pretty much like this for public encryption schemes, not like that, but what I'm going to describe. And they'll, sort of, people will submit these proposals. Other people will try to hammer it and attack it. And in 3 years, they'll kind of settle on a standard. Then we'll actually know what that N is, for real, in the sense, this is the N that the internet will use. Yeah. This is something that that we still don't know how to attack, but we have to wait for 3 years. That said, if any of you want to try your hand at breaking these, there are 64 proposals. Yes, out of which maybe about 25 are lattice-based proposals, so LWE-based proposals. And if there are 25 of anything, they cannot all be good. There has to be sort of rotten apples in there. Yes? So if any of you want to try your hand at like breaking stuff, which is always fun, if you ask me, you should come and talk to me. Okay. All right. So public encryption. Now I have 4 minutes. I only need 4 minutes. Public key. All right. So we don't quite have time to let you come up with it. In fact, I bet you will come up with something close to what I'm going to say, given sufficient time. So the public key is the following. Is this something I can do? So I have to tell you a fact, which at this point you have no choice but to trust me on this, which is, if in LWE I said the secret comes randomly from ZQ to the N, yes? That's the way things are defined. What if I choose the secret from each element, each coefficient of the secret from something else? Let's say randomly 0 or 1, or randomly from -2b plus 1 to 2b plus 1. The same thing that I do for the arrow. What happens? Turns out, quite magically, that LWE, where S is drawn at random from -2b plus 1 to 2b plus 1, and also the error, we're both drawn at random from this, is as secure as LWE, where the secret is drawn from randomly from ZQ to the N, and the error is drawn randomly from -2b plus 1. If this uses strictly less entropy than this guy. Here the secret is totally random, and here it comes from some other domain, the same domain as the arrow terms. Nevertheless, you can show that a reduction in both directions. And as usual, the reduction in one direction is trivial, the other one is not. So, the bottom line of this, now I have 2 minutes, is trust me that this guy is actually secure. When the error is small and the secret is small, then the view is still okay. So now let me show you the scheme. Then I pick a public key, which is a random matrix, n by n matrix, yes, and s times a plus e. We call it by definition e. Then s and e are both drawn from this world, not this world. What is the secret key? The secret key is s. How do I encrypt a message? This is going to look very familiar to you. If it doesn't, well, so I'm going to pick R, which is also like S. Like S, E, R, F, all these things are small, random small. Okay, Okay, they wrote down a whole bunch of things. All these guys, S, E, F, R, and prime, they're all small numbers. Either small numbers or vectors with small coefficients. Okay? You can do this by yourself, the errors, but let me, you know what? Given that I have 1 minute, let me erase the errors, which makes it completely insecure, but never mind. Yes? Very good. What is B in a product R? B, the vector in a product, B, row vector in a product R, the column vector, right? B is, by the way, S times A. Times R. That's what it is. Yes? So S, you should think about it as a row vector, A is a matrix, and R is a column vector. So S times A is a row vector, A times R is a column vector, B in a product R is a number. S times A times R is a number. Now do you see how to decrypt? Well, I give this ciphertext, yes? I have A times R, I have S. So I can compute S times A times R, which is this guy, so subtract from here. What you get is the message times Q. Now when you do it with errors, you will actually not get the message times Q plus 1 over 2, but that plus an error. Then you have to do the same tricks. That's the... This should look to you like the Diffie-Hellman scheme. S times A plus an error. A is like the G, the generator G in the Diffie-Hellman. This is like G to the power S. This is like G to the power R. And this is like G to the power RS. Yes? So take the Diffie-Hellman idea, you can instantiate it with LWE. You have to work a little harder because the errors, right? This is good. That's over. But that's really all I want to say about LWE for the moment. But you should keep these things in mind, not just for your problem set, but for the finale, grand finale class, where we'll come back again here.